Let's start with the title, because I owe you the truth before anything else. It says the experts are silent. And I have to be honest with you, that part isn't true. The scientists who study Yellowstone are not silent. They are, in fact, some of the loudest, most talkative scientists on Earth about their subject. They monitor that caldera with hundreds of instruments, every hour of every day. They publish constantly. And the overwhelming message they are shouting, if you actually listen, is reassuring. So if you clicked hoping to hear that geologists are secretly hiding an imminent catastrophe from you, I am going to disappoint you right now in the first 30 seconds, because there is no such secret. But stay with me, because there is a real question buried underneath the hype. And it is a question the experts genuinely do not get asked often enough. It is not whether Yellowstone is about to erupt, because it almost certainly is not. The real question is this: if the extraordinarily unlikely ever did happen, what would actually break first? What would fail fastest and reach the most people? And the answer surprises almost everyone, because it isn't the lava, and it isn't even the ash burying entire towns. The thing that would collapse first and fastest across the largest number of people is the electrical power grid. And which states go dark first is not a mystery, and it is not a matter of opinion. It follows directly from the physics of ash and from actual computer models built by the United States Geological Survey. So let's walk through it honestly, and by the end you'll understand something genuinely important about how fragile the grid really is. Something that matters far beyond Yellowstone. But first, the reassurance. Because it is real, and you deserve to hear it plainly. A full Yellowstone super eruption is one of the least likely disasters you will ever hear a video made about. The United States Geological Survey puts the annual odds of 1 at roughly 1 in 730,000. To put that in perspective, you are vastly more likely to be struck by lightning many times over than to see Yellowstone produce a super eruption in any given year. And that popular line you've heard, that Yellowstone is overdue, it's a myth. It comes from taking the 3 enormous ancient eruptions, roughly 2.1 million, 1.3 million, and 640,000 years ago, and averaging the gaps between them to invent a schedule. But 3 data points do not make a schedule, any more than 3 buses make a timetable. Geologists are clear. Yellowstone is not overdue. There is no cycle it is violating. And there is no sign whatsoever of an impending eruption. The system is far, far more likely to produce a small steam explosion, or a slow lava flow like the ones that last happened around 70,000 years ago, than a continent-shaking blast. So this is not a prediction. It is a thought experiment. But it's a thought experiment worth doing, because the vulnerability it exposes is completely real, and it applies to ordinary survivable eruptions too. So let's build the scenario properly, starting with the ash, because the single most important thing to understand is where it would actually go, and almost everyone gets this wrong. When people picture a Yellowstone eruption, they imagine ash blowing east on the wind, like a smoke plume. A long fan streaming across the Midwest. And for a normal, ordinary volcano, that's exactly right. The ash rides the prevailing winds downwind. But a super eruption does not behave like a normal volcano. And this is the crucial finding of the USGS modeling, published by scientists Larry Maston, Alexa Van Eaton, and Jacob Lowenstern. An eruption that colossal injects such an unimaginable volume of ash so high into the atmosphere, so fast, that it forms something called a continent-scale umbrella cloud. And an umbrella cloud does not drift downwind. It spreads outward in every direction at once, driven by its own force, powerful enough to push ash westward against the prevailing winds in north and south, in excess of 1,500 kilometers. In the words of the lead scientist, the eruption makes its own winds, strong enough to overcome the normal weather patterns of the entire continent. So the map that results is not a fan pointing east. It's a bull's eye. catastrophic depths of ash near the caldera, thinning steadily outward in all directions. The USGS models put it in concrete terms. You would see deposits measured in meters, that's multiple feet of ash, across the northern Rocky Mountains. You would see centimeters to decimeters, that's inches to a couple of feet, across the northern plains in the upper Midwest. And you would see millimeters, a dusting, reaching all the way to both coasts, potentially graying the skies over New York and Los Angeles alike. We know these models are realistic because we can check them against the ancient eruptions. The 640,000-year-old blast left over 3 meters of ash as far away as north-central Texas. So the ash doesn't just go one direction. It goes everywhere. And that is why the question of which states lose power isn't as simple as the ones downwind. Now here is the heart of it, the part the experts really don't get asked about, and the part that genuinely surprised me when I first learned it. You would assume it takes a massive, burying load of ash to knock out power. It does not. It takes almost nothing. And to understand why, you have to understand two things: what volcanic ash actually is, and how a power grid actually holds electricity in place. Volcanic ash is not soft, fluffy campfire ash. It is pulverized rock and volcanic glass, hard, sharp, abrasive, and microscopic. And crucially, its particles are coated in soluble salts and chemicals from the volcanic gases. When that ash is dry, it's mostly an abrasive nuisance. But the moment it gets wet, from dew, from fog, from a light drizzle, those surface salts dissolve, and the ash transforms into something electrically conductive. It becomes in effect a thin film that electricity wants to travel through. Now think about how the power grid works. Every transmission line, every substation, relies on insulators, those stacks of ceramic or glass discs you've seen holding the wires away from the metal towers. Their entire job is to keep the electricity trapped on the wire, separated from everything else by a gap of clean, dry air and porcelain. That gap is the only thing standing between an orderly power line and a violent short circuit. So now, coat those insulators with a thin film of wet, conductive volcanic ash, and you have just handed the electricity a path it was never supposed to have. It arcs across the surface of the insulator in a sudden, destructive electrical discharge. Engineers call it a flashover. And here is the number that should stop you. A flashover can be triggered by less than 3 millimeters of ash. Some studies put the critical threshold at just 1 millimeter if it covers enough of the insulator. 3 millimeters. That is a light dusting, the kind of coating you could wipe off with your hand. That is all it takes to make a high voltage line flash over, trip offline, and in the process burn and crack the equipment. When this happens across a whole grid at once, the effect cascades, line after line trips out, substations short, and the protective bushings on transformers. Some of the most expensive and slowest to replace equipment in the entire system. Crack and fail. Damage that can take months to repair. And this is not theoretical. It is exactly what happened, on a smaller scale, when Mount St. Helens erupted in 1980, and again in New Zealand in the 1990s, when ashfall from Mount Ruapehu caused shorting on power lines and disrupted electrical equipment across an entire island. Flashover is the single most common way volcanic ash causes blackouts, and it needs only a whisper of ash to do it. And flashover is only the first of 5 distinct ways ash attacks a power system, all of them documented by the USGS. The second is that ash destroys the power plants themselves. It gets sucked into the air intakes and cooling systems of generators and clogs them. In gas-fired turbines, it can melt inside the engine and grind down the blades, and it contaminates the water that plants rely on for cooling. The third is almost darkly ironic. Even where the equipment survives, utilities are forced to deliberately shut down lines and substations just to clean them, because you cannot safely wash live, ash-covered high-voltage equipment, so the cleanup itself means planned blackouts. The fourth is slow, but relentless, because the ash is essentially powdered glass. It abrades and corrodes every exposed moving part it touches, wearing the system down. And the fifth is brute force. Once the ash gets heavy, more than about 4 inches deep, its sheer weight overloads and snaps the power lines outright, collapses poles and light structures, and drags ash-laden trees down onto the wires. So put those two facts together, and you understand the whole picture. A thin dusting of ash, just millimeters, trips the grid offline through flashovers, fast, across a huge area. And a heavy fall, inches or feet, doesn't just trip the grid, it physically buries and destroys it. Which means the states that would lose power first and worst are simply the states that get the most ash. So let's name them, grounded in that USGS bull's eye. Number 1 is Wyoming, and this one is not really in question, because the caldera itself sits inside Wyoming. Under a super eruption, Wyoming's grid isn't damaged. It's entombed, under meters of ash, along with nearly everything else. Number 2 is Montana, directly adjacent to the north. The southern half of the state, including its larger population centers, would be under a punishing load of ash, meters near the border thinning to feet further out, more than enough to bury and break the transmission network across the region. Number 3 is Idaho, immediately to the west. And here is where that umbrella cloud matters, because a normal westward wind would spare Idaho, but the umbrella cloud pushes ash west regardless. Burying eastern Idaho under a heavy fall the ordinary weather would never deliver. Number 4 is South Dakota, out on the northern plains, where the models show centimeters to decimeters, inches to a foot or more. Remember, it takes 3 millimeters to trigger flashover. South Dakota would get that many times over, meaning its grid trips offline across the entire state, fast. Number 5 is North Dakota, just to the north, in a nearly identical situation, its power network shorting out under a fall of ash vastly greater than the sliver required to bring it down. Number 6 is Nebraska, spanning the Central Plains, receiving centimeters to decimeters of ash and losing its transmission grid the same way, through cascading flashovers across a state-sized area all at once. And number 7 is Colorado, where the ash reaches into one of the most densely populated corridors in the interior West, the Front Range and the Denver Metro. Even a fall of a few centimeters, or less once it's wet, is more than enough to send flashovers cascading across a major metropolitan grid serving millions of people. Now, I have to be honest about the caveats, because that's the whole point of this channel. The exact ranking would depend on the precise size of the eruption and the wind patterns on the day it happened. And because the ash spreads as a bull's eye rather than a plume, the truer picture is concentric rings of destruction, not a neat top 7 list. States like Utah, Kansas, Minnesota, and Iowa would be hit hard too, just at the outer edges of the worst zone. But these 7, the Northern Rockies and the Northern to Central Plains, sit unambiguously in the heart of the impact. And the essential, non-obvious point holds for all of them. Even the states catching only a few centimeters get far more ash than the tiny amount it takes to trip an entire grid offline through flashover. They would not lose power over days. They would lose it in hours. And here is what turns a blackout into a genuine catastrophe. It would not be a quick fix. A normal blackout gets repaired because crews drive out, swap the broken parts, and restore power within hours or days. In this scenario, none of that works. The roads are buried under ash that turns to a heavy concrete-like sludge the moment it rains. The helicopters and planes you'd use to survey the damage from above are grounded because ash destroys jet engines. The very same reason a single, far smaller Icelandic eruption shut down European air travel for days back in 2010. The replacement parts, especially the giant high-voltage transformers, take months to over a year to manufacture even in normal times, and utilities keep only so many spares. And because the grid is all interconnected, the failure doesn't stay contained. As the Ashfall states drop offline, They drag on the neighboring regions, spreading instability outward. So in the worst-hit states, this is not a blackout you wait out over a long weekend. It's a loss of power measured in weeks or months, all while the ash is simultaneously contaminating the water, collapsing roofs, stopping every car, and grounding every flight. But now let me bring this back to Earth, because this is where the thought experiment stops being doom entertainment and becomes genuinely useful. You do not need a Yellowstone super eruption for any of this to matter, and that is the real, under-discussed lesson hiding inside the whole question. The exact same physics, wet ash on insulators causing flashovers, took down power at Mount St. Helens and in New Zealand from ordinary survivable eruptions, the kind that actually happen. There are dozens of active volcanoes sitting near populated areas and power grids all over the world, in the Cascades of the Pacific Northwest, in Iceland, in Indonesia, in Japan, in the Andes, any one of which could put a few millimeters of ash onto a regional grid and cause exactly this kind of flashover blackout, on a smaller and far more plausible scale, at essentially any time. So the Yellowstone scenario is really just a giant magnifying glass held over a small, quiet, entirely real vulnerability. The electrical grid that our entire modern civilization depends on can be tripped offline by a few millimeters of a substance that any explosive volcano on the planet can produce. That is the thing the experts don't get asked about enough. Not the Hollywood fantasy of a supervolcano, the ordinary fragility that the fantasy accidentally reveals. So let's end where honesty demands we end. Yellowstone is, tonight, almost certainly not going to erupt in your lifetime, or your children's, or your grandchildren's. The scientists watching it are not silent. They are not frightened, and neither should you be. That is the truth, and no amount of dramatic music changes it. But somewhere out on the northern plains right now, in the dark, a transmission line runs across the open grass, held up by a slender string of ceramic insulator discs. Each of those discs is keeping tens of thousands of volts exactly where they belong, separated from the metal tower and the ground below by nothing more than a few inches of clean, dry porcelain and air. That insulator has done its silent job, invisibly, for decades. It would keep doing it through a thunderstorm, through a blizzard, through the hottest heat wave. The one thing it could not do its job through is a dusting, just 3 millimeters of wet volcanic ash. And that is the real lesson hiding inside the Yellowstone question. Not that a supervolcano is coming for us, because it almost certainly is not, but that the vast, humming, invisible grid we have built our entire way of life upon can be undone by something as thin and as gray as a film of dust, from any volcano, anywhere on Earth. The experts who could tell us this